Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Here we will learn about different concepts related to civil engineering. Time to enter the world of civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about transportation engineering, horizontal alignment. Horizontal alignment is one of the most important features influencing the efficiency and safety of a highway. A poor design will result in lower speeds and resultant reduction in highway performance in terms of safety and comfort. In addition, it may increase the cost of vehicle operations and lower the highway capacity. Horizontal alignment design involves the understanding on the design aspects such as design speed and the effect of horizontal curve on the vehicles. The horizontal curve design elements include design of superelevation, extra widening at horizontal curves, design of transition curve, and setback distance. Design speed. The design speed, as noted earlier, is the single most important factor in the design of horizontal alignment. The design speed also depends on the type of the road. For example, the design speed expected from a national highway will be much higher than a village road, and hence the curve geometry will vary significantly. The design speed also depends on the type of terrain. A plain terrain can afford to have any geometry, but for the same standard in a hilly terrain requires substantial cutting and filling, implying exorbitant costs as well as safety concern due to unstable slopes. Therefore, the design speed is normally reduced for terrains with steep slopes. For instance, Indian Road Congress, IRC, has classified the terrains into 4 categories, namely plain, rolling, mountainous, and steep based on the cross slope as given in Table 1. Based on the type of road and type of terrain, the design speed varies. The IRC has suggested desirable or ruling speed as well as minimum suggested design speed and is tabulated in Table 2. Table 1, Terrain Classification. Terrain classification. Cross slope, percent. Plain. 0 to 10 rolling. 10 to 25 mountainous. 25 to 60 steep. 60. Table 2, Design speed in as per IRC, ruling and minimum. Type: plain rolling hilly. Steep NSSH 100-80 80-65 50-40 40 30 MDR 80-65 65-50 40 30 30 20 ODR 65-50 50-40 30 25 25-20 VR 50-40 40 35 25-20 25-20. Horizontal curve. The presence of horizontal curve imparts centrifugal force, which is a reactive force acting outward on a vehicle negotiating it. Centrifugal force depends on speed and radius of the horizontal curve and is counteracted to a certain extent by transverse friction between the tire and pavement surface. On a curved road, this force tends to cause the vehicle to overrun or to slide outward from the center of road curvature. For proper design of the curve, an understanding of the forces acting on a vehicle taking a horizontal curve is necessary. Various forces acting on the vehicle are illustrated in the figure. They are the centrifugal force, P, acting outward, weight of the vehicle, W, acting downward, and the reaction of the ground on the wheels, R. A and R. B. The centrifugal force and the weight is assumed to be from the center of gravity, which is at h units above the ground. Let the wheel base be assumed as b units. The centrifugal force P in kgm2 is given by P equals W times V2/G times R, equation 1, where W is the weight of the vehicle in kilogram. V is the speed of the vehicle in meter per sec. G is the acceleration due to gravity in msec2a and d. R is the radius of the curve in meter. The centrifugal ratio or the impact factor P/W is given by P/W equals V2/G times R. The centrifugal force has two effects: a tendency to overturn the vehicle about the outer wheels and a tendency for transverse skidding. Taking moments of the forces with respect to the outer wheel when the vehicle is just about to override, pH equals W times B/2. P/W equals B/2 times H. At the equilibrium, overturning is possible when V2/G times R equals B/2 times H, and for safety the following condition must satisfy: B/2H V2/G times R, equation 2. The second tendency of the vehicle is for transverse skidding, i.e., when the centrifugal force P is greater than the maximum possible transverse skid resistance due to friction between the pavement surface and tire. The transverse skid resistance, F, is given by F equals F A plus F B equals F times R A plus R B equals F times W, where F A and F B is the Schnell force at tire A and B. R A and R B is the reaction at tire A and B. F is the lateral coefficient of friction and W is the weight of the vehicle. This is counteracted by the centrifugal force, P, and equating P equals F times W or P slash W equals F. At equilibrium, when skidding takes place, from equation 1. P slash W equals F equals V2 slash G times R, and for safety the following condition must satisfy. F V2 slash G times R. Equation 3. Equation 2 and 3 give the stable condition for design. If equation 2 is violated, the vehicle will overturn at the horizontal curve, and if equation 3 is violated, the vehicle will skid at the horizontal curve. Analysis of superelevation. Superelevation or cant or banking is the transverse slope provided at horizontal curve to counteract the centrifugal force, by raising the outer edge of the pavement with respect to the inner edge, throughout the length of the horizontal curve. When the outer edge is raised, a component of the curve weight will be complemented in counteracting the effect of centrifugal force. In order to find out how much this raising should be, the following analysis may be done. The forces acting on a vehicle while taking a horizontal curve with superelevation is shown in figure. Forces acting on a vehicle on horizontal curve of radius r in meter at a speed of v in msec2. R. P. The centrifugal force acting horizontally outwards through the center of gravity. W. The weight of the vehicle acting downwards through the center of gravity, and F. The friction force between the wheels and the pavement, along the surface inward. At equilibrium, by resolving the forces parallel to the surface of the pavement, we get P cos equals W sin plus F A and F V equals W sin plus F times R A and R V equals W sin plus F times W cos plus P sin, where W is the weight of the vehicle, P is the centrifugal force, F is the coefficient of friction, is the transverse slope due to superelevation. Dividing by HOCOs, we get PCOs slash W cos equals USN slash HOCOs plus F times HOCOs slash HOCOs plus F times sin slash HOCOs. P slash W equals tan plus F times P times tan slash W P slash W 1 minus F times tan equals tan plus F P slash W equals tan plus F 1 minus F times tan. Equation 1. We have already derived an expression for P/W equals V2/G times R. By substituting this in equation 1 we get V2/G times R equals 10 plus F 1 minus F times 10. Equation 2. This is an exact expression for superelevation. But normally, F equals 0.15 and 4 degrees, 1 F10. 1 N for small, 10 sin equals E/B equals E, then equation 2 becomes E plus F equals V2/G times R, where E is the rate of superelevation, F the coefficient of lateral friction 0.15, V the speed of the vehicle in MSEC2, R the radius of the curve in meter, and G equals 9.8 MSEC2. 3 specific cases that can arise from equation 3 are as follows. If there is no friction due to some practical reasons, then F equals 0 and equation 3 becomes E equals V2/G times R. This results in the situation where the pressure on the outer and inner wheels are same, requiring very high superelevation E. If there is no superelevation provided due to some practical reasons, then E equals 0. And equation 3 becomes F equals V2/G times R. This results in a very high coefficient of friction. If E equals 0 and F equals 0.15, then for safe traveling speed from equation 3 is given by V. B equals V F times G times R, where V B is the restricted speed. Design speed plays a major role in designing the elements of horizontal alignment. The most important element is superelevation, which is influenced by speed, radius of curve and frictional resistance of pavement. Superelevation is necessary to balance centrifugal force. Now, we are going to discuss about the design of superelevation and how it is attained. Guidelines on superelevation. While designing the various elements of the road like superelevation, we design it for a particular vehicle called design vehicle, which has some standard weight and dimensions. But in the actual case, the road has to cater for mixed traffic. Different vehicles with different dimensions and varying speeds ply on the road. For example, in the case of a heavily loaded truck with high center of gravity and low speed, superelevation should be less, otherwise chances of toppling are more. Taking into practical considerations of all such situations, IRC has given some guidelines about the maximum and minimum superelevation, etc. These are all discussed in detail in the following sections. Design of superelevation. For fast-moving vehicles, providing higher superelevation without considering coefficient of friction is safe, i.e. centrifugal force is fully counteracted by the weight of the vehicle or superelevation. For slow-moving vehicles, providing lower superelevation considering coefficient of friction is safe, i.e. centrifugal force is counteracted by superelevation and coefficient of friction. IRC suggests following design procedure. Step 1. Find E for 75% of design speed, neglecting F, i.e. 1 equals 0.75 V, 2/G times R. Step 2. If E 1 equals 0.07, then E equals E 1 equals 0.75 V, 2/G times R. Else if E 1 greater than 0.07, go to step 3. Step 3. Find F 1 for the design speed and max E, i.e. F 1 equals V2/G times R, E equals V2/G times R 0.07. If F 1 0.15, then the maximum E equals 0.07 is safe for the design speed, else go to step 4. Step 4. Find the allowable speed V. For the maximum E equals 0.07 and F equals 0.15. V A equals V 0.22 times G times R. If V AV, then the design is adequate, otherwise use speed adopt control measures or look for speed control measures. Maximum and minimum superelevation depends on A. slow-moving vehicle and B. heavy loaded trucks with high CG. IRC specifies a maximum superelevation of 7% for plain and rolling terrain, while that of hilly terrain is 10% and urban road is 4%. The minimum superelevation is 2 to 4% for drainage purpose, especially for large radius of the horizontal curve. Attainment of superelevation. Elimination of the crown of the cambered section by rotating the outer edge about the crown. The outer half of the cross slope is rotated about the crown at a desired rate such that this surface falls on the same plane as the inner half. Shifting the position of the crown. This method is also known as diagonal crown method. Here the position of the crown is progressively shifted outwards, thus increasing the width of the inner half of cross-section progressively. Rotation of the pavement cross-section to attain full superelevation by There are two methods of attaining superelevation by rotating the pavement. Rotation about the center line. The pavement is rotated such that the inner edge is depressed and the outer edge is raised both by half the total amount of superelevation, i.e. by E/2 with respect to the center. Rotation about the inner edge. Here the pavement is rotated raising the outer edge as well as the center such that the outer edge is raised by the full amount of superelevation with respect to the inner edge. Radius of horizontal curve. The radius of the horizontal curve is an important design aspect of the geometric design. The maximum comfortable speed on a horizontal curve depends on the radius of the curve. Although it is possible to design the curve with maximum superelevation and coefficient of friction, it is not desirable because realignment would be required if the design speed is increased in future. Therefore, a ruling minimum radius r. Ruling can be derived by assuming maximum superelevation and coefficient of friction. R ruling equals V2/G E plus F. Ideally, the radius of the curve should be higher than r. Ruling. However, very large curves are also not desirable. Setting out large curves in the field becomes difficult. In addition, it also enhances driving strain. Extra widening. Extra widening refers to the additional width of carriageway that is required on a curved section of a road over and above that required on a straight alignment. This widening is done due to two reasons. The first and most important is the additional width required for a vehicle taking a horizontal curve, and the second is due to the tendency of the drivers to ply away from the edge of the carriageway as they drive on a curve. The first is referred as the mechanical widening and the second is called the psychological widening. These are discussed in detail below. Mechanical widening. The reasons for the mechanical widening are, when a vehicle negotiates a horizontal curve, the rear wheels follow a path of shorter radius than the front wheels as shown in figure. This phenomenon is called off-tracking, and has the effect of increasing the effective width of aeroed space required by the vehicle. Therefore, to provide the same clearance between vehicles traveling in opposite direction on curved roads as is provided on straight sections, there must be extra width of carriageway available. This is an important factor when high proportion of vehicles are using the road. Trailer trucks also need extra carriageway, depending on the type of joint. In addition, speeds higher than the design speed causes transverse skidding, which requires additional width for safety purpose. The expression for extra width can be derived from the simple geometry of a vehicle at a horizontal curve as shown in figure. Let r 1 is the radius of the outer track line of the rear wheel, r 2 is the radius of the outer track line of the front wheel. L is the distance between the front and rear wheel. N is the number of lanes, then the mechanical widening W. M, refer figure, is derived below. R 2 equals R 2 plus L2. R 2 equals R 2 plus L2 equals R 2 minus W M 2 plus L2 equals R 2 minus 2R 2 W M plus W M2 plus L2 2R 2 W M minus W M2 equals L2. Therefore the widening needed for a single lane road is W M equals L2 slash 2R 2 minus W M 1. If the road has n lanes, the extra widening should be provided on each lane. Therefore, the extra widening of a road with n lanes is given by W M equals NL2 slash 2R 2 minus W M 2. Please note that for large radius, R 2 R, which is the mean radius of the curve, then W M is given by W M equals NL2 slash 2R 3. Psychological widening. Widening of pavements has to be done for some psychological reasons also. There is a tendency for the drivers to drive close to the edges of the pavement on curves. Some extra space is to be provided for more clearance for the crossing and overtaking operations on curves. IRC proposed an empirical relation for the psychological widening at horizontal curves. W PS W PS equals v/2.64 vr, 4. Therefore, the total widening needed at a horizontal curve W EIS W E equals W PS plus W M W E equals v/2.64 vr plus NL2/2r. In India, the design of superelevation follows IRC guidelines wherein the initial design is done by considering 75% of design speed and the safety of design is assessed. Pavement is to be given extra width at curves to account for mechanical and psychological aspects. Now in next section we will deal with the design of transition curves and setback distances. Transition curve ensures a smooth change from straight road to circular curves. Setback distance looks in for safety at circular curves taking into consideration the sight distance aspects. A short note on curve resistance is also included. Horizontal transition curves. Transition curve is provided to change the horizontal alignment from straight to circular curve gradually and has a radius which decreases from infinity at the straight end, tangent point, to the desired radius of the circular curve at the other end, curve point. There are 5 objectives for providing transition curve and are given below. To introduce gradually the centrifugal force between the tangent point and the beginning of the circular curve, avoiding sudden jerk on the vehicle. This increases the comfort of passengers. To enable the driver turn the steering gradually for his own comfort and security. To provide gradual introduction of superelevation, and to provide gradual introduction of extra widening. To enhance the aesthetic appearance of the road. Type of transition curve. Different types of transition curves are spiral or cloudhoid, cubic parabola, and lemniscate. IRC recommends spiral as the transition curve because it fulfills the requirement of an ideal transition curve, that is, rate of change or centrifugal acceleration is consistent, smooth, and radius of the transition curve is infinity at the straight edge and changes to r at the curve point, L. S. 81/R, and calculation and field implementation is very easy. Length of transition curve. The length of the transition curve should be determined as the maximum of the following 3 criteria: rate of change of centrifugal acceleration, rate of change of superelevation, and an empirical formula given by IRC. Rate of change of centrifugal acceleration. At the tangent point, radius is infinity and hence centrifugal acceleration is 0. At the end of the transition, the radius r has minimum value r. The rate of change of centrifugal acceleration should be adopted such that the design should not cause discomfort to the drivers. If c is the rate of change of centrifugal acceleration, it can be written as c equals v2/r minus 0/t equals v2/r L 2v equals v3/L S times R. Therefore, the length of the transition curve L S1 in meter is L S1 equals V3/C times R, where C is the rate of change of centrifugal acceleration given by an empirical formula suggested by IRC as below. C equals 80, 75 plus 3.6 V. Subject to C. Min equals 0.5. C. Max equals 0.8. Rate of introduction of superelevation rays, E, of the outer edge with respect to inner edge is given by E equals E times B equals E, W plus W. E. The rate of change of this rays from 0 to E is achieved gradually with a gradient of 1 in over the length of the transition curve, typical range of NIS 60 to 150. Therefore, the length of the transition curve L S2IS L S2 equals N times E times W plus W. E. By empirical formula IRC suggests the length of the transition curve is minimum for a plane and rolling terrain. L S3 equals 35 times V2/R, and for steep and hilly terrain is L S3 equals 12.96 times V2/R, and the shift SAS S equals L S2 24ths times R. The length of the transition curve LS is the maximum of equations 1, 3 and 4 OR5I.E. LS equals max L S1L S2L S3. Setback distance M, or the clearance distance, is the distance required from the center line of a horizontal curve to an obstruction on the inner side of the curve to provide adequate sight distance at a horizontal curve. The setback distance depends on sight distance, OSD, ISD, and OSD. Radius of the curve, and length of the curve. Case A, L, S, C. For single-lane roads, A equals S/R equals 180 times S slash P times R. A2 equals 180 times s slash p times r. Therefore, m equals r minus r cos a 2. For multi-lane roads, if d is the distance between center line of the road and the center line of the inner lane, then m equals r minus d cos 180 times s slash 2p r minus d. M equals r minus r times cos a 2. Case A. LSLC for single lane roads. M 1 equals r minus r times cos a 2. M 2 equals s minus l c slash 2 times sin a 2. The setback is the sum of m 1 and m 2 given by m equals r minus r times cos a 2 plus s minus l c slash 2 times sin a 2, where a 2 equals 180 times l c slash 2p times r. For multi-lane road, a 2 equals 180 times s slash 2p r minus d, and m is given by r minus d cos a 2 plus s minus l c slash 2 times sin a 2. Curve resistance. When the vehicle negotiates a horizontal curve, the direction of rotation of the front and the rear wheels are different. The front wheels are turned to move the vehicle along the curve, whereas the rear wheels seldom turn. This is illustrated in figure. The rear wheels exert a tractive force T in the peak direction. The tractive force available on the front wheels is Tkosa in the peace direction as shown in the figure. This is less than the actual tractive force, T applied. Hence, the loss of tractive force for a vehicle to negotiate a horizontal curve is CR equals T minus T cos A. Summary. Transition curves are introduced between straight road and circular curve. Setback distance controls alignment around obstacles at intersections and curves. Vehicles negotiating a curve are subjected to tractive resistances due to the curvature. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.